This is the first Intro to Topology call. I'm Thomas, also known as Gyozi Gyoza on Twitter. And today we are going to talk about the past, the present, and the future of topology. So the TLDR of what happened in the past few years is that we went from building everything on chain to opening the Pandora's box of distributed computing over peer-to-peer networks. And a year later, Topology Protocol was born. We will tell you about everything that happened. First, the past. So the entire project or the company or the mission started with this single thought, which is if code is law on a blockchain, then smart contract is the ink that legislates the laws. And the law of a digital space is its digital physics, right? So if you want to create digital spaces that are truly sovereign, you ought to use the ink, the smart contract ink, to legislate its digital physics. And this is directly quoting from a blog post that we have on blog.topology.gg. So if you want to check out the blog post, go to that website. So we started the journey with smart contract ink that legislates the digital physics, and we started by making physics simulations. So on the left, you can see October 17, 2021, we did physics simulations in Cairo smart contracts that runs on StarkNet. And these are physics simulations, or to be more precise, these are numerical simulations that compute how these bodies rotate and interact with each other according to the laws of physics. And on the right, and this was 2022, 2023, we did a fully asynchronous fighting game where every single frame is calculated in the Cairo VM. All these physics, hitboxes, overlapping, calculating the friction, the gravity, and so on, everything is computed in the Cairo VM. So we're really trying to write digital physics of virtual worlds or simulations within the smart contract. But then we have been struggling with something that I think anyone who has worked with any blockchain would realize, which is a blockchain is not exactly very fast. One of its limitations is you have this notion of transaction, you send a transaction, you wait for transactions to confirm, you then do the next transaction, right? There's a waiting that is involved in the process. If you play modern video games, there's not a lot of waiting involved. You play the game, you feel live, it's very interactive and dynamic. A blockchain doesn't give you that feeling. So we wanted to find out the kind of digital physics and the virtual worlds that make sense to run on chain, and we arrive at this pattern called the local first pattern. The local first pattern is the idea that you run the smart contracts not on chain, but on your computer locally. You still run the same VM, running the same smart contract logic, but you're just running in your own machine. And you send the results of these computations to the blockchain, and these results interact with other people's results, where other people also run their smart contracts on their machines. So we still use the smart contract ink to run digital physics, right? We're just moving the execution from the blockchain to everyone's machines locally. And that's the local first pattern. And Shoshin was such a fighting game. It is an asynchronous fighting game where the fighting or the design of the fighting strategy and the fighting simulations is not happening on the blockchain. It runs in the Cairo VM, but it runs locally in players' browsers. But then we were really enticed by the pain that why can't we do things in real time? So the fact is, we wanted to find the theoretical underpinnings, like exactly why, scientifically, why we can't do things really fast. Then we arrive at this thought, or this observation of our universe, which is light doesn't move very fast. Or we use speed of light as something that goes really fast. This light travels 3 to 10 to the 8th meters per second. That's pretty fast. Actually, that's the fastest speed you can ever reach in the universe, but it's pretty slow considering how fast our CPUs run, our machines run. So every time your CPU tick, I mean, a modern CPU, light only travels 4 inches in length. But if you have players that are spread across the world, they are separated by many, many inches, way too many inches. It really takes time for information to travel, even at speed of light. Considering that, and also considering what we really want to do is we want to be able to be online at the same time, to feel the presence of each other and to be able to interact and collaborate in real time. That is really difficult if we consider that light doesn't travel very fast, and we don't have anything that travels faster than light right now. So that brought us to the discovery of CRDT. The idea of CRDT is a kind of data that abstracts the internet within itself. It is a strange concept, but if you think about the internet, if picture a whole bunch of machines that are connected and talking to each other, and you shrink that entire image into a dot and you put it inside a piece of data. Okay, if you're with me, that piece of data is powered by the internet within itself. And what does that do? This piece of data coexists across the internet, and it allows everyone on the internet to edit and collaborate on the same piece of data all at once. That's what it means by CRDT. It has this full name of conflict-free replicated data types, and we're not going to the technical in this call. But what it really means is multiplayer data types, or it's a data type that really abstracts the internet within itself. You're putting the internet into the data. Okay, so this is a wonderful structure for data to run over a whole bunch of machines at the same time. It is a data type that's built for distributed systems natively. Okay, so we fell in love with CRDT the day of discovering CRDT. This was sometime in April 2023. Since then, we did a bunch of things such as tinkering with YJS. So YJS is a free open source JavaScript library that allows anyone to create web apps using CRDTs. And so we wanted to understand how CRDTs work. We created this called the Penguin World, which is a 2D platformer game lobby where every player is represented as a penguin. And this recording here you're seeing was from a session where our colleagues were playing at the same time. And by playing, we do not log into anyone's server. We do not even call any one of our machines as a server and everyone else as clients. This is truly peer-to-peer. This is just my laptop and the laptops of all of my colleagues connected over peer-to-peer, and we're constantly sharing what we see of the Penguin world, and we're constantly doing things to it in real time. I think this was 30 frames per second. So imagine an input rate of 30 times per second. That is the speed at which this runs per user. And we're constantly exchanging our view of the Penguin world, and we're constantly merging them. And because of CRDT, or conflict-free, these merges never conflict. They always merge with success. And so the universe just moves forward, incorporating all information, and everyone's looking at the Penguin world unfolding, incorporating actions made by other people smoothly and without conflicts. So this is P2P, and this is computation over P2P. There's no server involved, there's no blockchain involved, and all the peers are equal. No special peer is rendered as a server where everyone else connects to. Okay, so we learned a lot from this experiment, and we were really excited. But then there was really rabbit holes after rabbit holes behind CRDT. See, CRDT is not an invention that came out of the vacuum. It came from years of trying to work with databases across computers connected by the internet or connected by any communication channels. And the rabbit hole is really, really deep. in this screen alone, you can see Redis, which is a database service that uses CRDT. You can see the Hacker News title where people are discovering, oh, Apple Notes uses CRDT behind for synchronizing Apple Notes between devices. On the bottom, you can see Atom Teletype, that is their code editor, uses CRDT for people to code together in the editor. You have databases built on CRDT, and you have Jupyter Notebook, which is a collaborative notebook for programming, usually in Python, and people build data science projects together. That also uses CRDT for people to collaborate in real time. And there's even more than that. So if we dig into the bottom of CRDT, we run into the wall of databases, distributed systems, and PGP networks. And these are amazing rabbit holes that we indulge ourselves in. So let's give some of the protocols a shout out. So this was 1980, and this is called Usenet. This was before I was born, and Usenet basically was a decentralized news service protocol. So in the middle of this picture, you see 3 big computers. Remember, this is 1980s, so personal computing revolution just happened very recently back then. We don't have smartphones anyways. We don't have a lot of machines like nowadays. So we have these few machines in the middle, and they are constantly asking these end users that are logging in from their terminals. So these are small screens on the peripheral of the picture. These are the users. They have less powerful screens that are just used to connect to the bigger machines in the middle. And they can publish news, right? Users can write news articles. These machines in the middle are constantly asking for new news articles, and also their topic, under which topic is the news article published. And they're constantly exchanging these news articles with respect to topics so that any user interested in any topic can eventually get the news articles published under those topics. And this is a protocol built on the UUCP, Unix to Unix copy protocol, that works between the Unix machines. And this was so many years ago. But I think if we take a step back, the computing revolution was only 60 years ago. We're only 60 years into the computing revolution. So this entire computer thing is still young. A lot of imagination is, and design spaces are still available. Right, so then fast forward to 1989, we have the World Wide Web, or nowadays we just call it the web. The World Wide Web is a simple concept. So a lot of people have files and books and pictures and informations, and we want to use the magical internet to share information with everyone else. How do we do that? Okay, so the guy who wants to share information is the server. The guy who wants to request for information is the client. And every piece of information is given a URI or a name. Okay, and information is structured as an HTML, and the information travels between computers following the protocol called HTTP. And all these names are names that we use every day, right? These are household names. But back then it was super new, and back then it wasn't even the only hypertext protocol for structuring and sharing information online. There were dozens of protocols like this created by universities and institutions. But the web succeeds, and now anyone who has a machine goes online, typically goes on the web and get information from the web, right? So we're pretty successful at proliferating the web, and this is nice. But then, if you look at the web, information is served by a server into a client. What if the server goes down? The information ceases to exist, right? So it's not super robust in the sense that the existence of a piece of information is rely on the survival of the server. Okay, so what about Napster? The Napster thing is the idea that, hey, I have a piece of music in my computer, and I want to share it with my friend. But I don't want to run a server. I hope that there is a protocol for me to share my music with my friends. And also I hope that all my friends can connect together and we can all share the same virtual pool of music. And if I'm looking for some music, and I can ask all my friends if anyone has them, and if they have it, they can share it with me. And vice versa, I'll reciprocate the effort. If they ask for music that I have, I'll also share it with them. And that gives you Napster. Napster is this P2P network where everyone is a client and you have a catalog which records who has which file. And so if I am asking for a music file, I go to the catalog and ask who has that file, and it might say, oh, Alice and Bob has that file. I'll say, okay, I'll go ask Bob. Bob, give me that file, and then Bob will transfer that file P2P to me. Okay, so this is a P2P network, but it has a choke point. That is the catalog thing, right? The catalog is a big machine that everyone go ask first. Who has the access of the file before they go directly to the person. And so Napster was shut down because the catalog thing is a physical computer that somebody has to operate in real life, and it's at a fixed location, and it's easy to discover, and therefore subject to regulations. And this thing is really provocative because this thing helped proliferate pirate music and just content piracy in general. People can share content without permissions, and it is a liberating but also a dangerous tool. Right? Freedom is a two-edged sword. And so what happens after the Napster is BitTorrent. The BitTorrent gives you multiple things on top of Napster. So first of all, BitTorrent basically allows files to be shared between peers. That's same as Napster. But what's different is you don't just go on this network and ask for files. If you ask, you also need to give. You need to reciprocate the effort to the network. Otherwise, you can't ask for files. BitTorrent wants the network to be as symmetric as possible between the givers and the and the askers, so that the network is healthy. And it also has other mechanisms to make the catalog in this picture decentralized, in the sense that catalog is no longer a single machine that everyone go ask, and it has trouble such as governments can find them, and also it has finite bandwidth, so it can clutter. It also has efforts to decentralize that, so you don't have to go to a single machine to ask who has the file, and the network is more healthy for sharing files. And BitTorrent to this date is still being used for sharing a lot of files, files that typically are not well suited for Web2 commercialized big platforms to build a business for. You have a lot of these files being shared on BitTorrent because it's a freedom technology, quote unquote. Okay, fast forward to 2014, we have IPFS, and anyone in Web3 should have heard of IPFS. IPFS is still trying to answer the question, I want a file, give me the file, where can I find the file? But it's trying to solve this also without relying on a server, right? So it has a P2P network, and these are IPFS nodes, and they can have possession of contents, and these contents are identified by their CID, their content ID, which is just a string, a very long string. But this mapping is unique in the sense that if you give a CID, it uniquely identifies a file and no others. And these files are being redundantly held by a lot of IPFS nodes on the network that are constantly talking to each other, so that when you ask for a file, if someone has the file, with high probability you can get the file. So you don't have to rely on server be online, and there's no centralized catalog where you have to go ask. A lot of these systems are decentralized and made into protocols, so that IPFS to this day is when you feel cute and you want to make a decentralized applications, you will say, hey, I made my decentralized applications and my images and my files are not IPFS. That's what you do. And that just speaks to its success in the decentralization space. When you want to have something decentralized, host in a decentralized manner, the first thing to think about is I'll put my file on IPFS. Now, something different here is called braid. And I think way less people in Web3 has heard about braid. But this is a really interesting protocol. So IPFS gives you the ability to declare the existence of a file and for people to ask where's the file. Braid is not about files anymore. It is about real-time synchronization. Braid basically says HTTP is just for transferring web pages. But nowadays, we don't use web just for transferring web pages anymore. We go on the web to be together with someone else and to collaborate with someone else in real time. So Braid wants to be this protocol that extends HTTP into a synchronization protocol, no longer a transfer protocol, a synchronization protocol. And on the left, this GIF shows the structure of the history of an HTTP under the Braid protocol. And it looks like a graph, right? This graph basically describes what everyone did to the HTTP file as a single graph. And these people that are collaborating on the same HTML file, they will have these pictures recording the history of the file, and they will be seeing the exact same file. So this allows people to collaborate in real time using the HTTP protocol, but extended with Braid. And this is still an ongoing effort at IETF, the last time I checked. Okay, but here's the thing. If you look at the history of these protocols, a lot of these protocols are trying to answer the question, where's the file? Where's the file on the internet? Where can I find the file? I think we will agree that nowadays, it is more interesting to ask, where's the world? Where can I find a world? And where can I join that world where other people are playing in, right? And a file in the world is fundamentally different. A file is a static piece of data. A world is a dynamic, evolving environment where things can change and be modifiable, potentially by many people at once. That's the fundamental difference. And so these are two very different problems, which brings us to the present. So Topology Protocol basically is like this. So IPFS gives you an MP3 file, right? You can ask for a file. Spotify doesn't give you a file. Spotify streams you the song directly, so you listen to the song. But what Topology does is it throws you into an unstoppable jam session with musicians connected all over the world, and your session is broadcasting tunes live and accessible to everyone on the internet. So see the difference? IPFS gives you the file. It's a static piece of data. Spotify streams you a song, but that is still a static piece of data, but it just streams you in real time. You don't have to wait for download to listen to the music. You can start listening as soon as you have the first batch of packets that you can reconstruct the music. Topology Protocol is about world. It's about people dynamically and in real time being in the same space, feeling each other's presence and doing things together. Another way to pitch Topology Protocol is it is like IPFS, but it is not for static files. It is for real-time multiplayer programs. And this is an example that we created for TS Topology, which is the TypeScript implementation of the protocol. And this was about a week ago. In this screen, you can see two clients connecting to the same 2D grid space. Each client is represented as a circle, and they're moving around, and they can see each other in real time. The only delay here is the network delay, is the delay of information travel from one client to the other client. That is the only delay. For those of you in Web3 space, we know about block time. We may know a little bit about block time. If you break down what's in block time, it's way more than network delay. There's a lot of waiting for going back and forth. People going back and forth confirming who can join the voting, who can vote. You're tallying the votes, you're counting the votes, you're waiting for the votes to pass. maybe you time out the voting period and you have to re-elect the leaders and so on. A lot of these situations, the weightings is making the block slow. It's fundamentally way longer than network delay. Here we're going back to the basics. Here, the only thing that we're not optimizing for is the speed of light and the internet backbone infrastructure. Unless we touch them, we cannot go below them, right? Speed of light is the extreme, is the limit of the universe for now. And internet backbone infrastructure is something that's super complex, and it is a completely different project to want to do something about it. But we stay on top of that, and we say, can we just do real-time collaboration while only being limited by infrastructure of the internet and the speed of light? And this is what it gives: real-time P2P collaboration between people. To delve in a little deeper, Topology Protocol gives you this new abstraction called CRO. So think of Ethereum. Ethereum gives you smart contract, and if you want to do anything on Ethereum, you make a smart contract, right? This is 2015. If you read the white paper, the first thing you think of is, I want to do something on Ethereum. What smart contract can I write? On Topology Protocol, if you want to create anything, you think about what CRO can I create? It is an object that carries the magic of CRDT. So CR is borrowed from CRDT, but you drop the data type and you replace it with object. That gives you CRO. And we are aiming for CRO to be the digital material for making multiplayer software, all multiplayer software in the future. So we really think of it as a material. It is a material that gives you certain affordances that you can use to create certain things. And some of these affordances including people can interact with things you create with this material in real time over peer-to-peer. You don't need to pay for servers or cloud bills for this piece of program to exist. People can join without permission if you want them to join, and so on. These are the affordances of this new material. And this also comes with a network called decentralized RAM. So decentralized RAM is an open P2P network where CROs live, and every one of these nodes on the decentralized RAM network is a topology node. Think of topology node as a container or a carrier that carries CROs, but it doesn't just carry a CRO. It carries a copy of the CRO, because these CRO, they're not a single entity. They exist in the form of a whole bunch of copies, one user per copy, right? So in this diagram, you can see Alice, Bob, and Charlie, the three guys on top. Each of them has the purple diamond CRO, or CROD. So CROD doesn't just live on one person's machine. It exists in copies, and Alice, Bob, and Charlie each has a copy of D. And they're doing things simultaneously to this CRO, and they're exchanging what they did to each other so that they remain synchronized. And this happens peer-to-peer. Neither Alice nor Bob nor Charlie is special than any other. They're equal peers. So this is dRAM. Okay, I think that if we want to invent a new protocol, we have to ask the question, why does this world need a new protocol? And I think this year is a special year where there is considerable fatigue and doubts and uncertainty about where Web3 can go, and this is not just reflecting the market the market situation, but also reflecting perhaps the kind of use cases that are coming up in the Web3 space that are not matching our enthusiasm years ago. So let's go back to the very famous critique of Web3 by Moxie, the founder of Signal. So he wrote this critique of Web3 back in the beginning of 2022. And you can find this, this blog still lives online. And you can find this blog, and if you go down to the bottom of the blog, it gives you two recommendations. Moxie provided two recommendations. The first one is, Moxie said we should accept the premise that people will not run their own servers. servers is just hard to maintain. It's difficult to run. And every full node on Ethereum is expected to be a server, and it's difficult to operate a server. Therefore, last time I checked, there were less than 30,000 Ethereum full nodes in the world. That may be outdated, but I think it's at the correct order. And 30,000 is far from the population of Earth that I think the Web3 is really targeting. It's the population of Earth, of humans. And there's a reason to that. It's difficult to operate server. It's difficult to be offline all the time. There's memory requirements and all that stuff. So Moxie recommended we accept that we'll have to do centralized client-server connections, and we'll have to use cryptography to solve it, to solve the trust issues. So don't try to decentralize everything, except that we will have servers, but we will use cryptography so that the power of the server is reduced. Okay, so we are proposing an alternative. We're saying we're not asking everyone to be clients, just be clients. We're also not asking everyone to be servers, but we're asking everyone to run a topology node. And literally everyone, not the professional guys that know how to run machines and have perfect uptime all the time. Everyone, and you can run your topology node in your browser. You can run a topology node per tab in your browser. And it is supposed to just work magically. So here's how it works. This 3 lines of code is all you need to get a topology node running, right? So you import it, you spawn it, and you start it. That's it. So the distance between any browser and a DRAM network is just 3 lines of code. You get a topology node, and it basically wraps around libp2p. For those of you who have heard about libp2p and Protocol Labs, topology node wraps around libp2p node and provides a set of friendly abstractions, and it just magically works. Okay, so 3 lines of code get you on DRAM. That's the deal. The second thing that was recommended by Moxie in the critique is we should try to reduce the burden of building software. See, we're only 60 years into the computing technology, and the number of people in the world that build software is way less than the number of people that don't know how to build software still. And also Moxie said distributed system is complex. He said, unfortunately, I think distributed system have a tendency to exacerbate this trend by making things more complicated and more difficult, not less complicated and less difficult. So he's basically saying, if creating software is difficult, creating software that runs over distributed systems or many computers at once is even more difficult. But we're suggesting that this may change with Topology Protocol. So this is our goal. We say we're providing CRO as an abstraction. And the valid proposition is that CRO is like an apple for making an unstoppable real-time multiplayer app. It's so easy to play with. It's so easy to reason about and create, even by yourself, that anyone of the future should be able to create multiplayer software just working for them. The concept here is just working for them is fine. You can have an application with a user base of 1 or user base of 3. You don't need to scale to 10,000 or 100,000 or 1 million users. You can create software for a user base of 1 and 3 and 5, and it makes sense because it's so easy to create. If we go back to this example, this super basic 2D grid example that was released a week ago, this application was the basic scaffold and the shape of this application was created under 30 minutes. And I was creating this by hand. Only that I wasn't creating this by hand. I was creating this in the cursor code editor. So what I did is this. I feed the cursor code editor with the chat example that's also on TS Topology, our open source implementation of the protocol in TypeScript. And I asked cursor, okay, so study the chat CRO so that you understand how CRO works and how topology protocol works. Okay, and then once you understand, generate me a CRO of a 2D grid space where users can log in and they show up as circles. And they can move around, up, down, left, and right with their arrow keys. at integer units, and they can see each other because the CRO synchronizes. This was not verbatim, sorry, but this was roughly what I told the code editor to do. And the result is the CRO for this application is just 100 lines of code. If you go to GitHub, I'm not lying, if you check the source code of this CRO, it is literally just 100 lines of code. And it's very easy to reason. And if you look at the front end of this application, I think it's 300 lines of code with an additional 100 lines just for calculating the colors here. Because I wanted to make the colors relatively dark or below 50% luminance, so it's contrast nice over the white background. That alone costs 100 lines of code. Otherwise, this application front end is 300 lines of code. So it was really easy to create. And if you forget about CRO and the topology protocol, how typically you would create a multiplayer applications is first you would think about what database should I use, what backend should I use, what framework should I use for backend and frontend to talk to each other, what structure of the state on the front end should I maintain that maintains synchronized to the database on the backend. There are many pieces along this line you need to consider to make a network applications. But with topology protocol, the only thing you need to think about is I'll make a CRO and I'll make a front end application that renders what the CRO looks like and also takes user inputs and inject it into the CRO. That's all you need to do. It's a front end and a CRO. So now we're ready to talk about the future. And it's impossible to predict the future, but the job of ours is to define the future that we want and to actively work towards it, to actively create it. So what is the future that we're looking at? Well, we think the future we want is AI is really an important piece of technology, and AI is redefining the process of software creation, no doubt. With AI redefining how software is being created, Topology Protocol is defining what is the material of software, the composition of software itself. Where Topology Protocol is providing the material for all multiplayer software of the future. So AI is defining the process. CRO is the material, the substance you use that makes up of the software. On the left is Vision Pro from Apple official website. On the right is Meta's latest augmented reality glasses released less than a day ago, I think. The goal for Topology Protocol in a couple of years of time is this. I want to be able to say, hey, spawn me a model of my new house with gesture navigation control, and also ask my wife and kids to join me. And we'll explore some interior design styles together. I'm talking to an AI, wearing my virtual or augmented reality device all the time, and what's being created is a CRO. The AI says, okay, a CRO for your house has been generated and it is put on dRAM. And I am dialing your wife and kids now. So you guys can join, can look at the house model together and to discuss interior designs together. I think that is what we want, is for users to be able to summon multiplayer programs at will, to be able to connect to other people in these programs at will, and to be able to collaborate and feel the presence in real time. We think that is the future of Topology Protocol. And this is the future that we're actively working towards. Of course, there are a long list of uncertainties and dependencies that is really, really difficult. But we think that if we make CR really easy to create, if we reduce the complexity of making multiplayer applications by 10x or more, we can see a lot more multiplayer applications come up. And if you couple this with AI, and we think the future is really bright. Anyone can create multiplayer real-time objects and programs for themselves and their loved ones and their friends and their communities, and they can join at will, peer-to-peer, not censorable, not stoppable, not gateable by platforms and so on, and it just works. So if you're excited about the future and if you are not afraid of challenges, because building topology protocol is all about facing challenges, things that other people think is impossible or impractical or just not smart to do at all, and we do it. If you like that idea, you can join our Telegram, Topology Friends. You can also follow our GitHub, Topology Foundation, where you will find everything that we do is open source. TypeScript implementation of the protocol, among other projects. That's the presentation. I think we're ready for Q&A.
Nice, beautiful presentation. Thank you, Kitty. And we've had some reactions. How amazing the future looks like. If you have any questions, please drop them in the chat so we can make sure that you leave here knowing everything that you have to know. And yeah. So we have some new people joining us today. Maybe you have some questions about the basics. And we have some people who have been following the community for a long time. Did you know all of this? Let us know if something is new as well and you would like to explore more. And really the future, the ideation for the future is so cool. Looking forward for that. How far are we from that, by the way, regarding years or months maybe?
I think to answer that question, we have to ask Meta if they have their SDK available so we can tinker with. Yeah, there's a lot of dependencies to make this work end to end, but yeah.
Lucia said that this is new to me. I only knew up to the BitTorrent protocol, which I use daily. We have some people typing now.
I think for those of you who also want to fall into the CRDT rabbit hole, one place to start is this protocol, the Braid protocol, because I'm guessing a lot of you may not be very enjoying reading academic papers. So one way to dive into CRDT is to read the papers. But alternatively, you can dive into a protocol that wants to ship CRDT to the internet protocol suite. And you go through what they did, you catch the keywords that you don't understand, and you dig. You will open up a Pandora's box of distributed systems, like we did.
We had a comment from Oak asking when token. And and then Nom said that the latest blog post from ledgers to some customers is great. I think it's a succinct explanation for topology protocol coming from a blockchain point of view, global and infinitely scaling sandcastle. Okay, so we have a question from Oak. How was the transition from FOCG to P2P protocol?
Yeah, the transition is it was like a 180 turn, and we were really moving at really high speed because we were building this on the right. We were running a tournament at Stanford where people play our fully on-chain game but running in the Cairo VM in person. And we were thinking about design patterns and getting things to work with blockchain being a very slow global network in the middle. And then we took a hard 180 turn, and then we started to look at papers, and we started to dig into how distributed databases work and how data gets replicated across machines and how they can stay consistent and what protocols have been attempted. They are more than easily hundreds of them, commercialized or academic, trying to do this over past 2-3 decades. And it's not just databases as well, it's networking protocol involved. There's so many things here. It was basically jumping from making games to back to the library and just read books, and there are hundreds of books and papers to read. But I think it was a really wonderful period because we didn't know that we would have come out with Topology Protocol at all. We just learned about CRDT and we knew that this thing is so elegant structurally, something that can be different at different places, but they can always merge and become the same. It's just a very beautiful concept and has some similarity with how our universe works when it comes to space-time. And we could not resist but jumping into the rabbit hole and just absorb everything we can find. And also, we know that not everything should live on chain. And I think it's still a narrative to try to put everything on chain. And I can relate to that spirit. We being part of the movement to try to do more things on chain, not less. But blockchain had its fundamental limitations. And once you realize these fundamental limitations and you realize there are alternatives to run computations over peer-to-peer, but not in a blockchain way, you can never turn back. Once you know the existence of these theories and these approaches, blockchain no longer is the only way you do decentralized computing. So it was worth it, but during the process, it was a lot of uncertainty. It was literally traveling in a dark tunnel, not knowing where the exits are, or if there is an exit even. So it was a time of uncertainty.
And we had another question from Tini. Can topology unlock a new type of application?
Yeah, I think that I'll just go to the last slide. I think the new application we want to do is this. We want to be able to have multiplayer software that you can just summon on demand. I just summon, I want a multiplayer space for my friends to hang out in the next minute. Give it to me, and then a space is created. We can all jump in and interact in real time. And the entire process is not constrained by a platform or any platform. Because once you have platforms, you have policies, and they have their aesthetic standards and their UI kits and their programming language and their libraries and their license and terms of use. All that comes with platforms. And no platforms like to lose network effect. It's just how platforms survive in the world. But without platform, you can have customized software with user base of 1, user base of 10. It doesn't matter. Platforms want to resort to the massive possible user base because that gives them economy of scale. When you can just create personalized software or customized software just for you and your friends in your community, and you can use that in real time, P2P, in an unstoppable way, then I think that's really changing how we think about software even. And I think a lot of that is coupled with how AI is changing or redefining software. And I think we can't. I remember 2 years ago when the last bear market began to unfold, and LLMs began to take up steam. There were founders leaving crypto and going into AI, and there were discussions about people not having enough faith in Web3 and trying to go to the next big thing, which is AI at the moment. I think AI has gone through a lot of bull and bear cycles, and it has been going through cycles since many decades ago, since at least 1960s or 70s with cybernetics. So AI is a force to be reckoned with, and I think we're not even talking about decentralized learning or decentralized inference or anything that I think Web3 AI is currently discussing. We're just providing CRO as a new material for making multiplayer software, and it is a material that is very easy to reason about and robust and very easy to make. It is a simple material, so that we hope and we're aiming for in the future, when people create multiplayer software, possibly through AI, what the AI spits out is a CRO or CROs, a composition of CROs. This is what we're aiming for. We're aiming for the material that are useful for making multiplayer software.
We have one last question from Dudes. Do you think there would be regulations with this technology, like how the Europe, US regulation regulating social media?
Well, I think freedom is a two-edged sword, and if we allow more freedom, we are welcoming more diversity, and probably diversity that spills over what regulations are comfortable with or what regulations are happy about. And so that's just I think the fact of increasing freedom and increasing people's agency. And the implication of that is you sort of make regulatory bodies uneasy. But precisely how regulations may come in, I think it depends on if and how use cases pick up on CRO. So we're imagining a lot of these ideal use cases where people look at house models together and discuss interior designs together. But as people get more freedom, the first thing they want to do online with people may not be looking at houses and collaborating on interior design. There can be many possibilities, and I'm sure some of those possibilities are just frowned upon by current regulations. And so with progress, I think regulations catch up after progress. So I think this is a really good question in the sense that is the creator and the stewardship of a credible neutral protocol responsible for the social implications of the protocol? And I think this is a really difficult question that we must all face if topological protocol or when topology protocol create use cases that are at the next level of agency and freedom and new use cases that are making current social norms uncomfortable.
Nice, thank you. And I saw some people starting to type something and they stopped. If you have any questions, I think we are on top of the hour, but you can, if you really want, you can drop it. If not, we are on Telegram. I just shared the link with you, and you should definitely share the questions and comments and reactions there.
Nice. Just looking at the slide, I recall something I read from the original story of the web. I think between 1993 or 1994, the original creator crew of the web they were celebrating because they saw more than 100 servers on the web serving websites, and that was a milestone for them. 100 servers, 100 different websites. We can start counting how long until we have 100 topology nodes in the world. And I think we can create a dashboard just tracking topology nodes and visualizing them and the topology and so on. I think that would be pretty cool to see nodes popping up and disappearing. These nodes run in browser tabs or any machines that can run topology node, and it is expected to be ephemeral. So these nodes are not incentivized to stay online and punished by going offline. They come with the users and they follow the freedom of the user.
Yeah, we can start a betting system as well. How fast until we get to 100 and then to 1000, and so it goes exponentially. Nice. Hmm. Well, I think this was a great first session of Introduction to Topology. Great to hear about the story behind the protocol, where we are going to, and where we are right now. So, thank you everyone who joined. It's great having you and hope to see you around. And thank you, Guti, for the presentation as well. I think you're checking the chat right now, right? Yeah. Nice.
Yeah, thank you everyone for coming to the first Intro to Topology call. I think we're scheduled for an hour, so we are already over time. We hope that this call is interesting to you, and join our Telegram chat. We can discuss more there.
Yes, and contributions are open. Oak just said, and they are on Only Does. You can find Topology Protocol there. Thank you, everyone.
Have a good morning, good night, good afternoon.